Hey there. So you want to do some oh, let's see. Yeah. Absolutely. Like identifying the oxidizing agent, reducing agent, um and like balancing redox equations type stuff. Okay, solid. Yeah, here. We can cook something up. Let me just look up a couple values here real quick. Then we'll brew something up. Here, hang on one sec. Ah. Here, hang on. Okay, here. Oops. Oh, hang on one second. Sorry about that. There we go. Okay. Okay. So for all of these problems, um, we're going to identify the oxidizing agent, reducing agents, and we are going to write a balanced chemical equation for the redox reaction. So let's go ahead and start with a reaction between manganese 2 and BiO3 with a charge of -1. And this becomes permanganate and bismuth 3. All right. So the thing to remember when you are balancing redox reactions is that well first let's figure out oxidizing reducing agents. I think that'll be an easier place to start. And I'm going to actually reduce this in size just a little bit. Oops. There we go. There we go. All right. So first step, we want to assign all of our oxidation states, and then we're going to look for changing oxidation states to identify our oxidizing agent and reducing agent. So manganese will have an oxidation state of +2 because it has a charge of +2 and it is the only element present in this species. Same with bismuth. Actually, I apologize. This should be a +3, not a negative. So we know that manganese on the reactant side is +2, and bismuth on the product side is a +3. Now we have to do a little more legwork to figure out bismuth on the reactant side. So we know that the oxidation state of bismuth plus 3 times the oxidation state of our oxygens has to equal the total charge on our species, which is -1. We don't know the oxidation state of bismuth, but oxygen, and this is the final rule in the 4 for assigning oxidation states. Oxygen is the most electronegative element, so it's going to pick up its regular an oxidation state equal to its normal ionic charge, which is a -2. So we know that the oxidation state of bismuth plus 3 times the oxidation state of oxygen is equal to -1. So that means bismuth minus 6 equals -1. And so we can find the oxidation state of bismuth by adding a +6 to both sides. And we get bismuth is equal to, has an oxidation state equal to +5 on the reactant side. So we have a +5 for bismuth and then a -2 for oxygen. Now we have to do the same, give manganese the same treatment on the product side. We know that the oxidation state of manganese plus 4 times the oxidation state of oxygen equals our total charge, which is -1. And again, oxygen is the most electronegative element in this species, so it is going to have its regular ionic charge for its oxidation state, -2. So the oxidation state of manganese plus 4 times -2 equals -1. That means the oxidation state of manganese -8 equals -1. Now we add 8 to both sides, and we find that on the product side, manganese has an oxidation state of +7. All right, so now that we've assigned all of our oxidation states, we need to identify which ones are changing. And we can see that the oxidation state of manganese changes. It goes from 2 to 7. And the oxidation state of bismuth changes. It goes from +5 to +3. So bismuth goes from a +5 to +3. That means bismuth has gained electrons, right? It's picked up 2 negative charges to go from a +5 to a +3. So bismuth, because it's gained electrons, is reduced. Now let's look at manganese, the other species that changed. It goes from a +2 on the reactant side to a +7. All right, that means that manganese is, it's gone from a +2 to a +7. It's lost negative charges, which means it is oxidized. All right, so we've identified which element is oxidized and which element is reduced, but we have to ask the question, okay, we know bismuth is, whoa, that's a very bright yellow. I'm not a fan. We'll use this. Bismuth is reduced. But the question remains, what does bismuth react with that causes the reduction? And the answer is manganese 2 is the reactant that reacts with bismuth to cause the reduction. So Mn2 plus is the reducing agent. All right. We're going to do the same process for manganese. We know that it is oxidized, but what species reacts with manganese causing that oxidation? And the answer is, the reactant is BiO3 with a negative charge. Is the reactant causing that oxidation? So we say that BiO3 minus is the oxidizing agent. All right? So that is how you assign oxidizing agent and reducing agent. Ah, that is, yes, no. That is, sorry, I said yes and no. It's a confusing answer. That is completely correct. That will be true every time. All right. You'll notice that the element that is oxidized, bismuth, is inside the element that is reduced is inside the oxidizing agent, and the element that is oxidized is inside the reducing agent. That will be true every time. They flip identities. Totally, that is a great observation. Yeah, totally. So that's one of the skills that you need. We also need to be able to balance these things, and that will require us to follow the half reaction method. All right, and just as by way of reminder, the half reaction balancing using the half reaction method is step 1. Step 1, you have to split your reaction into 2 half reactions. Then you have to balance the atoms. Whoops. You balance the atoms. You balance the charges. Then you balance the electrons. And then step 5, you recombine. All right, that is, those are the 5 steps of the of balancing using the half reaction method. And we're going to do it here first. So step number 1, we have to split our reaction into 2 half reactions. One half reaction involves manganese. The other half reaction involves bismuth. So we're going to take one half reaction, balance its atoms, charges, and electrons. Do the same for the second half reaction, and then we're going to recombine them. So one half reaction will be, we're missing one piece of information before we can balance this situation. So we need to know the conditions. Conditions can either be acidic or basic. We're going to say that the conditions of this reaction are acidic. So this redox reaction takes place under acidic conditions. All right, so let's take our manganese half reaction where we have Mn2+ becoming MnO4-. All right, first off, we need to make sure all of our atoms are balanced. And if we line up our atoms, we have 1 manganese and 0 oxygens on the reactant side. On the product side, we have 1 manganese and 4 atoms, oxygen atoms on the product side. Now, manganese is balanced, but oxygen isn't. Now, the way you balance oxygen atoms in a redox reaction is all of these reactions take place in aqueous media. There's water everywhere. So whenever you have a disparity in oxygens, you add water molecules. So we are going to add, let's see, we need 4 oxygen atoms, so we're going to add 4 molecules of water. And now on our reactant side, we have 4 oxygens and 8 hydrogens, which is great except for the hydrogens part, right? We have 8 hydrogens on the reactant side now and none on the product side. So we need to bring in 8 hydrogens to balance. And you do this when you're in acidic media using hydronium ions, H plus ions. We need to add 8 of them. That way our atoms balance. So now our atoms are balanced for our manganese half reaction. Just going to scoot this over a little bit. So we balanced our atoms. Now we have to balance our charges. And the way you balance charges is you can only do so by adding electrons. You can add electrons to the reactant side or product side. To figure out which, we have to look at the total charge because our total charge on both sides of this reaction have to be equal to each other. One of the things you'll notice is, so we look at the charges on our reactant side. We have a +2 from manganese and then nothing else. On the product side, we have a -1 from permanganate and 8 +1s from our hydronium ions. So the reactant side has a total charge of +2, but the product side has a total charge of +7. We need these two sides to be equal to each other. All right, we need them to be equal to each other. We can only add electrons, so we can only make one side of this reaction more negative. So you take the more positive side and add the number of electrons you need to make these two equal. And 7 is 5 bigger than 2. So we're going to add 5 electrons to the product side. So now we have -1, +8, -5 from the electrons. And if you add these all together, it now adds up to a +2. And now the total charge on both sides of this equation is equal. We haven't experienced a change in charge. So we have, at this moment in time, balanced the atoms and charges for the manganese half reaction. We need to do the same thing for the bismuth half reaction. All right. So let's look at our bismuth half reaction here. All right. So let's balance our bismuth. First, we got to start with our atoms. We have bismuth and oxygen. We have 1 bismuth on both the reactants and product side. We have 3 oxygens on our reactant side and none on our product side. The way you fix that is by adding 3 molecules of water. This balances our oxygen but introduces hydrogen. We know how to balance hydrogen, though. We bring in 6 hydronium ions, and now our atoms are completely balanced. After balancing our atoms, we need to balance our charges. And on our reactant side, we have +6 from our hydronium and -1 from our bismuth oxide situation. Bismuth oxide. I'm sure it has a special name that I just don't know. So this, on our reactant side, we have a total charge of positive 5. Oh, there's my mistake again. This is not bismuth minus 3. It is bismuth plus 3. Here we go. So we have a total charge of positive 3 on the product side. We need to bring this positive 5 down 2 clicks by adding 2 electrons to the reactant side. Now we have negative 2 plus 6 minus 1. This will all add up to a positive 3. And now the charge on both sides of this half reaction, charges are equal. All right. So we balanced, so at this moment in time, we have split, we've balanced our atoms, we've balanced our charges. Next, we got to balance our electrons. So here's our bismuth half reaction. All right. So here is our magnesium half reaction, or not magnesium, excuse me, manganese half reaction. All right. Let's talk about balancing electrons. All right. This comes from the fact that we said, you'll remember from lecture, when I was introducing redox reactions, I said that redox reactions were like a drug deal. It's a trade of electrons, but you never see them, right? They're never out in the open. That means that the number of electrons produced by one half reaction needs to equal the number of electrons being consumed by the other. You can't have any electrons left over in your reaction, not on the reactant side or the product side. So the number produced must equal the number consumed. Now you might be looking at this going, how's that going to work? Because 5 and 2 don't go to each other evenly. What you got to do is this reaction that consumes 2 electrons, we need to multiply the entire thing by 5. This half reaction that produces 5, we need to multiply this whole thing by 2. Watch what happens. So, taking the top, we're going to multiply everything in here by 5. So, 2 times 5 would be 10 electrons, plus 5 times 6 is 30 hydronium ions. 5 times 1 will be 5 of the BiO3. 5 times 1 is going to be 5 bismuth 3 ions, and then 5 times 3 is 15. We're going to do the same thing down below. 2 times 4 is 8 water molecules. 2 times, or 1 manganese will be 2. And this will produce 2 molecules of permanganate. 2 times 8 is 16. 2 times 5 is 10. And now we've balanced our electrons and we are ready to recombine. We're going to recombine by adding both sides of this reaction together. Oh, wow. Okay, hang on. I gotta clean up the whiteboard. Oh, that's good enough. All right, I'm going to move this up. And just to be clear, I was like, what is this 30 OH plus? This is 30 hot H plus ions. All right. Now, when we add these together, we need to look for things that will cancel with each other. One thing, if you've done your job right, the number of electrons on the product side of the arrow will be equal to the number of electrons on the reactant side of the arrow, and those will cancel. Oh, shoot. Sorry, hang on. Started drawing in the wrong layer. Here we go. These 10 electrons will cancel these 10 electrons. But those won't be the only things that will cancel. One of the things you'll notice is we have 16 hydronium ions on the product side and 30 hydroniums on the reactant side. So we can cancel some of these. These 16 cancel out completely. And we'll cancel 16 of these 30, leaving us with 14 hydronium ions. We also have some amount of water that can cancel as well. We have 8 water molecules on the reactant side and 15 on the product side. So this 8 cancels 8 of these, leaving us with 7 molecules of water. So let's take a look at what we're left with. On the reactant side, we have 14 hydronium ions plus 5 bismuth, or BiO3 minus, plus 2 manganese, 2 ions, producing 5 bismuth ions, plus 2 permanganate ions, plus, and I'm a little bit out of room, so I'm going to scoot this over. Plus 7 molecules of water. This is the balanced redox reaction. Ah, totally, totally. Um, yeah, here, let me cook up a basic conditions problem. All right, let's see. There it is. Okay. Yeah, oh dude, totally, totally. Um all right, let me find a good basic problem. Okay. And you know, I'm glad we did the acidic one first because we'll get it, it's good to kind of get the reps in because the thing is the the basic one is only there's a slight difference in it, and you'll notice it's all the same kind of steps, the same flow. Um, but okay, so let's go with all right, let's do all right. So let's do the following one. We'll do zinc reacting with nitrate to produce this zinc hydroxide complex plus ammonia. And what we'll do with this one is we'll just do the balancing just to make sure that we have enough time to like actually complete it because assigning oxidation states and determining uh, reducing agent, oxidizing agent, um, I feel like is a little more straightforward. But we want to be sure to get the balancing in under basic conditions because that's probably the hardest thing that can be on this test. So let's go ahead and take a look. So step one, we got to split this thing into two half reactions. Um, so we go. Let's go ahead and tackle zinc first. So we got zinc becoming this zinc hydroxide. All right. Actually, I want to do the other half reaction first. We'll start with the nitrogen half reaction. The NO3 nitrate becoming ammonia. Right, NH3. Yeah. So first we got to make sure our atoms are balanced, and we have some clear atoms that are out of whack here because we have 1 and 3 for nitrogen and oxygen on the reactant side, and then we have 1 and 3 for nitrogen and hydrogen on the product side. Now, the way we balance oxygen, always acidic or basic conditions, you always use water So if we need 3 oxygens added, we're going to add 3 molecules of water. This will give us 3 oxygens. It also gives us 6 more hydrogens, right? Because 3 times 2 is 6. So total of 9. Now we need 9 H's on our reactant side. And even under basic conditions, the way you balance them at first is by adding hydronium. And technically our atoms are balanced here. All right, our atoms are balanced. But here's the problem. Hydronium only exists under acidic conditions. So whenever you add hydronium to your problem with basic conditions, you have to undo that by immediately adding 9 hydroxide ions to both sides. And it's 9 because we added 9 hydronium. However many hydronium you added, you got to add that number of hydroxides. Here's the reason why. There's this cool little thing that happens when you have 1 hydronium reacting with 1 hydroxide. It becomes 1 molecule of water. So when we have 9 hydroxides with 9 hydroniums, this turns into 9 molecules of water. Oops. So these 9 hydroxides combine with these 9 hydroniums to make 9 molecules of water. So 9 water plus nitrate produces ammonia. Oops. Plus 3 water plus 9 hydroxide. And you'll notice that we have water on both sides. So you can wait to the end to cancel, or you could cancel these here. I'm going to cancel them here so it's less writing. These 3 cancel with these 9 to make 6. Exactly. So we have our atoms balanced now, and we've worked through the challenge of basic conditions. Now we just got to balance charges like normal. So when you look at the charges on each side, we have a -1 on our reactant side from nitrate and a -9 on our product side from our 9 hydroxides. We can only add electrons to balance charges, and we need to make this side more negative, so we're going to bring in 8 electrons. So we have -8 minus 1 is equal to -9. And that is atoms and charges balance for our first half reaction. All right. So let's do the other half reaction now. So let me pull up the original problem. There we go. All right. Oh, which is, nope, right here. So this one actually has a little bit of a trick. There's a shortcut. The typical problem won't go this way, but it's something to be aware of if you notice the presence of hydroxides. So we have zinc, oxygen, and hydrogen. 1 zinc, and then on the product side, 4 oxygens, 4 hydrogens. You'll notice that these are OHs, and there's 4 of them. You can go straight to balancing your atoms if you just add 4 OHs right here. And that's it. for balancing atoms. We still have to balance our charges, though. So let's go ahead and look at our charges. We have -4 on the reactant side and just a -2 on the product side. That must mean that we need 2 electrons to balance our charges for the zinc half reaction. All right, so here's our zinc half reaction. We already have our nitrogen half reaction. So that's ugly. I'm gonna pull this up really quick. All right. Just gonna make this slightly bigger and scoot it up. So one of the things you'll notice when we compare these two together is the number of electrons we're dealing with here actually kind of works out. Our zinc half reaction is producing 2 electrons. Our nitrogen half reaction is consuming 8. We know that the amount of electrons produced must equal the amount consumed, but 2 goes into 8 evenly, so we only have to multiply by our first reaction. If we multiply everything in that first reaction by 4, we'll be able to add these up no problem, and that'll balance our electrons. So if we do that, 4 times 4 is 16. So 16 hydroxides plus 4 zincs. And then we go for zinc hydroxides complexes, and then 4 times 2 is 8. Now we're ready to add these two together. We have done our job right, so our electrons cancel. We don't have any water molecules that can cancel, but we do have some hydroxides. We have 16 OHs on the reactant side. We have 9 OHs on the product side. So these 9 will cancel, well, 9 of these. And what we get for our final balanced equation is 6 water molecules plus 1 nitrate plus 7 hydroxides plus 4 zinc atoms produce 1 ammonia plus 4 zinc hydroxide complexes. And that is our balanced redox reaction for this one, for basic conditions. So I actually redox problems are actually one of the harder ones to not well to do, but also to write as an instructor. Um, I can kind of make some up off the top of my head, but it's slower, and I kind of have to check a couple things going into it. But I found a really good practice worksheet that I'm actually gonna post to Canvas once office hours are done. Um, it was just both of the examples that I did came off of this worksheet. They have the solutions built in, so that's nice. Um, so I'm gonna post this to Canvas for extra, not for like credit, but extra practice, extra Redox practice. I think it'd be good. Um, totally, yeah. Just because, like, honestly, with these problems, it's just a matter of of getting enough reps in, and so like having kind of those that practice available is really what it all comes down to.